So to review what we've been doing in class, so we've been looking at the TX architectures, so the architectures of the transmitters. So the ones we were concentrating on so far were the polar architectures, and so we said that if the waveform is primarily phase modulated, then what we can do is you can ignore any distortion in the amplitude generated by the up converter, because really you are interested only purely in the phase of the output signal from the transmitter. And obviously if you look at it in the IQ domain, you will have both I and Q channels. This way of transmitting the signal may not be as efficient as doing it as processing the phase alone in the phase domain. The circuit we know of that operates in the phase domain is the phase lock loop. So we said we'll take a phase lock loop, and there are many ways, many parts of the phase lock loop where you can actually apply the phase modulation, and or where you have to apply the phase modulation. First of all, from either the input or the divide input of the PFD, if you look at the transfer function from either of these points to the output, okay, it is a low pass transfer function, and the transfer function also depends on the parameters of the loop. Okay, so if your modulation is a very slow modulation, let us say it has only maybe 10 or 20 kilohertz, you can just directly apply it at either the FREF node or the FDIV node, and it will go through the PLL and automatically get up converted by the PLL. Nowadays we know that most PLLs have fractional dividers which have sigma deltas inside them, and this sigma delta normally has the fractional number that actually goes into it. So depending on what exact frequency you want to achieve, you have a certain integer number and a fractional number, the division number, that goes into this divider, and along with this static number you can also give it a dynamic number which will decide how the division ratio varies, and therefore how the output phase varies, phase and frequency vary. Is that clear? Now if the phase modulation is wider than the bandwidth of the PLL, then you have to split it into two portions. The low pass portion goes in the same place where we have talked about so far. The high pass portion actually goes in here, okay, because from the input of the VCO to the output of the PLL, the transfer function is a high pass function, and therefore you should add the high pass transfer function, the high pass portion of the signal there. Obviously you will have to make sure to normalize the gain through the two paths, so that when you actually add the two signals at the output, it looks like an all pass function. The problem with this is that as you keep going to wider and wider bandwidth signals, and with larger and larger what is called peak to average ratio, okay, in which is a definition, which is an indication of how dense the signal is. If you try to pack in more and more modulation, then what happens is, even though the signal itself in the Cartesian domain may be limited to a certain bandwidth, you will find that if you try to split the signal from its I and Q components into its amplitude and phase components, you will find that the bandwidth of these two is actually much wider. Okay, the bandwidth of these two will be much wider than the original signal itself. Okay, so then what happens? Splitting such a signal into amplitude and phase and then recombining at the somewhere down the line would become very inefficient. The reason is, now both the amplitude and phase parts now need to be extremely wide band, first of all, right? Extremely wide band. Second, when applying such a wide band signal through a PLL, it becomes all the more difficult to ensure an all pass transfer function for such a wide bandwidth. For a moderate bandwidth, you can probably ensure an all pass transfer function, but the wider it gets, the tougher it becomes to actually ensure an all pass transfer function. So what you'll find is with many of these modern wideband signals such as wireless LAN or LTE and so on, you will find that pretty much IQ is the Cartesian upconverter is the default architecture of choice. Now, if you actually look at the Cartesian direct conversion transmitter, so you have your Xi and Xq that come from your baseband. So you have a baseband that creates the symbols, and those are converted into the analog domain. Okay, the digital bits are converted using a digital to analog converter. Maybe that goes through some filtering. After that, you have to upconvert the signal. What do you use to upconvert the signal? You use a mixer in the Cartesian domain. Because you are interested in only one sideband of the mixer, in the transmitter normally that would be FLO plus F baseband. Okay, you would try to have two mixers, one of them driven with the cosine, the other driven with the sine, so in phase and quadrature components, and you add those two and then amplify them. In this case, the power amplifier needs to be a linear power amplifier, because any distortion in either the amplitude or the phase of the power amplifier will cause distortion to both Xi and Xq. If you take a polar transmitter, so I showed an example of a polar transmitter here. I showed what is a phase signal. Suppose you have a narrowband signal, but there is information in both the phase and the amplitude. How would you recombine the amplitude and the phase? We have talked about the phase path in the polar transmitter. How would you recombine the phase with the amplitude? So, in the polar case, I have this, and somehow I have A of t. This is my amplitude. Okay? Here at the input of the PLL I only have phi of t. At the output of the PLL, what I have is something which looks like cos omega naught t plus phi of t. So this has already got upconverted to the phase of the VCO, phase of the PLL output. What next? I need to multiply these two, right? If in the polar transmitter, what I actually want is A of t cos omega naught t plus phi of t. That is the output of the overall transmitter. How do I multiply two signals? A 4-quadrant multiplier. Okay, at what frequency should this multiplier operate? This is an RF multiplier, right? So what kind of circuit would multiply? Okay, a mixer is a possibility, but then why even go to all this length of doing the phase modulation through the PLL? So as it turns out, there is an easier way to actually combine the two outputs. So let me actually take this down because it's easier to operate with it this way. Okay, so if you had information only in the phase of the signal, what would you do? You would just take this output, correct? This would be a nonlinear PA. This would be a saturated PA, so that the efficiency is very good. Okay. Now, if you have amplitude also, one way to recombine, actually maybe you don't know yet, but if you actually take a nonlinear power amplifier, okay, the effective gain, okay, is a function, or the output is a function of the VDD. Okay, the output is a function of the power supply. Especially if it's a highly nonlinear power amplifier, it is just going to go to VDD and the amplitude is going to be equal to VDD. Okay, so if I take a high gain power amplifier and drive it with a phase signal, output is just probably going to go to 0 and VDD and back, right? And information is purely in the phase of the signal. Now, if I actually make this some function of A of t, okay, then what I am doing is, earlier when VDD was constant, the envelope of the output was just VDD. Now what I am doing is I am applying an envelope onto the phase modulated signal. So I'll just call it the modulator. Okay. I'm going to apply that to the supply. Now the thing to remember is that if you actually have a delay in either the envelope path or the phase path which is not matched, okay, so let us say you had some delay here, you had some delay tau here, then the output signal is no longer what you wanted. You are actually applying an envelope with some delay to your phase signal. Now your signal is totally corrupted. Okay, so to keep the error vector magnitude under control, you have to be very careful to manage the delays between the amplitude and the phase path carefully. If you were to take the same signal in the Cartesian domain, it's a lot easier because xi and xq paths are going to be almost identical. Managing delays between those two paths is not a problem at all. This problem purely arises in polar modulators. Okay, so that is so far as polar modulators are concerned. Next we moved on to IQ modulators. We said we are going to take xi of t, xq of t, mix them up, combine them, send them through a linear power amplifier and then into the antenna. Finally, to interface the PA to the antenna, in either case, you will need either a TR transmit receive switch or a duplexer or diplexer or whatever you want to call it. Okay. And as we mentioned, the duplexer has a very specific behavior between these three ports. It allows output to go from the TX port into the antenna port. It allows input to come from the antenna port into the RX port. It gives very good isolation from the TX port to the RX port. What are the things of significance in a transmitter? We said linearity and efficiency are obvious. What became obvious after we started considering the behavior of a non-ideal duplexer is the fact that you need to worry about noise in the receive band, because the receive band is at a certain offset from the transmit band. This could be anywhere from maybe 10 or 15 megahertz to all the way to maybe 200 megahertz. However, in-band noise is not critical. Here you are not worried about things like the noise figure of the mixer, of the up converter, right? Noise figure of filters and so on. You are more worried about distortion. One other unique problem in transmitters is the problem of power amplifier pulling. So especially if you have TDD type systems where the power amplifier and maybe there is some part of the TX is switching on and off. What will happen is when this happens, the power amplifier, being a high power system, will be magnetically coupled or coupled through the substrate or coupled through the circuit to other portions of the circuit which may or may not be turned off. Specifically, we were interested in the PLL system because the PLL itself does not turn on and turn off because its transients are very slow. What happens is, when you don't turn off the PLL but you try switching the PA on and off, the PA, being a high power system, will shift the output of the PLL ever so slightly. And when this happens, you will see a frequency or a phase error, and you will see some settling time, and you will see some behavior like this for the EVM. Okay, this could very well be due to frequency error. You can also detect this by switching on and off. If you can independently observe the output of the PLL, the frequency versus time, you will be able to see something similar, where you will see it getting jerked whenever the PA is turning on and off. So the obvious solutions Okay, if it's through the supply, do not share the PA supply with the rest of the circuits. Okay, that's obvious. That's very easy because many times the power amplifier may be having a different supply altogether. It may need a much larger supply than the rest of your circuit. That is not a problem. Quite often you want to place maybe the PA on a different substrate. Maybe it's a separate IC by itself. That will be the best. If you place it physically far away, it will avoid magnetic coupling. That is also okay. We also discussed using a differential PA to make sure many of these coupling effects are much smaller. Then finally, if you really want to help it much further, even more, you can choose different frequencies for the power amplifier and the PLL. Now there are many ways in which you can achieve this. And one obvious brute force way is to actually use a heterodyne transmitter. Instead of using a direct conversion transmitter, you first upconvert it to one frequency omega 1. Okay. Then after that, you upconvert it to F1 plus F2, and you make sure F1 and F2 are far away from the power amplifier frequency, which is F1 plus F2, and you are probably doing very well already. Now, the problem with this is, obviously you are actually using one more set of mixers, you are using two band pass filters. Remember that this band pass filter needs to be very high Q, because this mixer is not a single sideband mixer. You get both omega 1 plus omega 2 and omega 1 minus omega 2. You will have to reject one of them. Luckily they are very far away, because if F1 and F2 are much smaller than F1 plus F2, hopefully F1 minus F2 will be far away. So that helps you. But remember that the transmitter has very strict emission specifications. So even if the frequency is far out, the power levels which you want, which you should not be transmitting at other frequencies, are typically 100 dB below what you really want to transmit if you are really far away. Okay. So what else can you do for the Cartesian PX to separate the PA and the PLL? Okay, so so we are specifically considering obviously one other way is to this is one way you can do. That is, don't do a heterodyne system, transmit system. You generate two frequencies and mix them together only for the LO, only to generate the LO. So that way you can still make sure that omega 1 and omega 2 are not directly related to the PA frequency, which is F1 plus F2. Okay, so this is one possibility. What else? Anything simpler? We don't want to be designing like two PLLs. Okay, so one thing you can do, you can try to use a frequency divider to change the PLL frequency. Now what you are doing is you are actually moving the frequency away, but remember that if you use a frequency divider, the PA frequency and the PLL frequency will still be harmonically related. Okay, so one other very common solution is to let's say divide by 2 or 4. Okay, I am showing a single sideband mixer this way. Okay, so this is one way you can separate it. So what this means is, in this case, so FPA equals, let's say I'll say FPCO by N. Obviously you don't want to keep making N very large, otherwise your PLL will become very difficult. But typically 2 or 4 times is very easy. It's also very easy to actually generate design a divide by 2 or a divide by 4 to operate at these frequencies. Now, the other reason why this has become a very popular choice is because the divide by 2 also gives you all 4 phases. Okay. Okay. The divide by 2, if you design a differential divide by 2 carefully, you can actually get very accurate 0, 90, 180 and 270 degree signals, which you anyway need for your mixer, for your single sideband mixer. Remember, your single sideband mixer requires cosine and sine, but it requires the differential inputs for cosine and sine. So this has become very popular. Now what you need to worry about? You need to worry about the second harmonic or the fourth harmonic of the PA pulling the PLL. Remember that the PA is actually outputting a lot of power, and normally the second let's say the PA is outputting 30 dBm. The second harmonic may be 20-25 dB below. So it is still significant. It's not very large, but let us say if it's 20 dB below, you are still outputting a second harmonic content of plus 10 dBm. Okay, so that's how much is that? 10 milliwatts. That is still significant enough compared with significant enough to pull the VCO, but by very little. You are probably not going to affect it too much. So pulling from PA harmonics is definitely possible. But normally this is not a huge concern, and obviously if you use a divide by 2, pulling will be worse. If you use a divide by 4, pulling will be better, right? Because the frequencies are further out, the harmonics will be smaller. Okay, so apart from that, if you look at the TX matrix, okay, so you have something called an emission mask. What does that refer to? What do you understand by emissions? So you're trying to transmit something, right? You're not supposed to be you're supposed to be transmitting exactly what you should be, and you should not be disturbing somebody else's transmission or reception. Okay, so at a particular frequency, let us say your signal looked like this. Okay, you will have a transmission mask spec which may say, maybe it will look something like this. I'm just giving you an example. Maybe there's no true emission mask which looks like this, but this is an example of an emission mask. It will tell you from, if you're transmitting at a frequency F, okay, at a frequency F0, then from this offset to this offset, the power level can be so much. Okay, after that the power level should not be higher, and from this offset to this offset, power level should not be higher than this. For example, you may not be allowed to have something like this standing out. Okay, you may not have, you are not allowed to have your emission spectrum which looks like this. Why is that? The really useful portion of the signal, remember the useful portion of the signal may only be here. That looks identical for both. But in the second case, you are actually disturbing somebody else. What would be the reason for the red curve? Non-linearity of your TX. Okay, if you are, for example, if your any portion of your TX transmitter is non-linear, you will start seeing what is called spectral regrowth. Okay, so what will happen is you are not only having the signal which you are trying to transmit, but maybe in the adjacent channels, in the adjacent frequencies, you are actually seeing that floor come up because of the non-linearity of your system.
Are these numbers absolute or
They are absolute numbers in certain cases. In other cases, they may be dBc. Okay. For example, in the case of the emission mask, they are absolute numbers. However, if you are interested in EVM of your signal, they will be relative. Okay. For example, you may say that at a particular offset from my signal, I need to have a certain number. Okay. That will tell you how linear your transmitter is and how much EVM you have. If you have higher than that, you might have a worse EVM because it's still in band. It still contains the signal you are trying to transmit. If it is an emission mask, all they are interested in is the absolute number. For example, they might tell you beyond, let us say, beyond 10, let's say beyond 100 megahertz from the signal you are trying to transmit, you should be below 100 dBm, minus 100 dBm. Let me just give you an absolute number like that. You have to, you have to meet that. Okay? Then you have what is called adjacent channel power, which also tells you how much power you are transmitting, but very specifically in the channel allocated to the adjacent user. Also called ACPR, you will see ACP, ACLR and so on. Adjacent channel leakage ratio, adjacent channel power and so on. All of these will be specified as integrated power numbers. Remember, because the modulated signal, you don't have a sinusoid, you have an integrated power. Or sometimes what is called output radio frequency spectrum. Spurs, right? We already gave an example of that. So, if your PLL or something else or some other, maybe the mixer or something else produces unwanted spurious tones, you can't have that. Okay, because obviously these can act as interferers for other people. So that's why you're not allowed to do this. Finally, you have noise in the receive band, which is significant. Because it can raise the RX input noise floor. And very specifically, it raises the RX input noise floor. This is all the more important in FDD systems, where you might end up desensitizing your own receiver. Okay, you can't have that. And depending on what the duplexer, let's say this is duplexer. Depending on what the duplexer isolation is from the transmit to the receive port, so you may have a certain isolation from here to here. It is very easy to calculate how much your receiver will get desensitized. What you have to do is maybe you have some power PT here. Okay, you have a certain isolation number I here. Okay. And maybe you have some certain phase noise number here at a certain offset. And obviously, both of these are functions of the offset frequency. Maybe at 20 megahertz from your carrier or 40 megahertz from your carrier, you have a certain phase noise. Okay? That will get attenuated by the isolation and arrive at the RX. What is the RX input noise floor? Forget about the bandwidth, it's minus 174 dBm per hertz. Remember that? You remember that? So the RX input noise floor is minus 174 dBm per hertz. Obviously when you try to calculate the integrated noise, you have to take into account the bandwidth and so on, but this is the absolute noise floor, okay, sparse spectral density. Now let us say this Tx raises this noise floor by a certain amount. Obviously if it raises it by 2 dB, automatically your signal noise ratio just got worse by 2 dB. You have added 2 dB to the noise figure of your receiver. If you don't want to degrade at all, it needs to be much lower. So let us say I put in a specification saying, let us say the PN Tx at the Rx, okay, should be minus 184. So that it raises it by maybe like 0.1 dB or something like that, right? Which is practically negligible. You will get that kind of variation with many other things. If you put in the specification now, this will tell you, this will help you derive what the specification is at the output of the transmitter. Because the minute you say it should not degrade it by a certain amount, let us say minus 184, then you will be able to derive what phase noise, absolute phase noise power you need at the transmitter, because you know the isolation, the worst case isolation of the duplexer, and you know what the maximum Tx power is. At that point your noise floor will also be maximum, right? And therefore you can calculate what the phase noise spec of the transmitter itself is at a certain offset. So that is the way you would work backwards. How much can you actually survive? How much desensitization can you actually survive at the receiver? What is the isolation of the duplexer? How much phase noise do you need at the transmitter output? And then you will just have to design the transmitter for this particular specification. Okay, so that is as far as transmitters are concerned. Any questions? There is really not a lot of detailed analysis we can do, because the transmitter in general is much simpler than the receiver. Really, in most cases you would end up using a direct conversion transmitter. You would have a baseband filter, an upconversion mixer. We have already looked at mixers before. You, depending on what the input is and what the load is, it's either an upconversion or a downconversion mixer. The power amplifier we will be seeing briefly at after we finish up VCOs, so we'll be seeing it later. But as far as the TX architecture goes, this is it. There's not a lot of there is some innovations you can do here and there, but more or less it is fairly well understood. Okay. Sorry, one last thing. I think we did cover this, but let me. Yes. The TX noise, of course, it will still be an issue, because what you transmit from one antenna can be received at the other antenna. Correct, but actually, normally the duplexer isolation will be much better than what you can get from one antenna to another, right? Because that will just depend on the spacing between the antennas. Okay, whereas this one, it's like a filter which filters out most of the signal in the TX band. One important thing: how do you characterize the linearity of the system? We talked about this. So we wanted to represent the let us say the amplitude distortion, or what is called the AM characteristic, okay, and the AM PM characteristic. Okay, as we mentioned before, you can't just look at the compression curve of the fundamental, because that will tell you about the amplitude distortion. Remember, if you a generalized nonlinear system, A1 VN. Correct? This is a generalized nonlinear system, but you can also have distortion. This looks only at amplitude distortion. If you actually are worried about the phase of the signal, you will need to represent. What do you need to do if you need to take into account phase distortion? This tells you about amplitude distortion, right? What would you do to represent phase distortion? Okay, so if you had a nonlinear system which you wanted to represent as a polynomial, let us say, right? How would you represent the system? Yeah, I understand you have to look at the phase. That is why I drew this AM/PM characteristic. So you may have something like this, right? But how would you represent the nonlinearity as a polynomial? Okay, so that is one way to do it. So let us say this was the amplitude, right? Huh? Correct. So if A0, A1, A2 are all complex numbers, that is another way to do it. Okay. So you can have a separate polynomial for the phase phi out. You can have a separate polynomial, or each one of these will be complex. Okay. That is another way to do it. But really what you are interested in is, if you actually vary the input voltage or the input power, how much does the phase actually change? Is the output phase a function of the input amplitude or the input power? Okay. If you were to characterize let us say if you take a transmitter and wanted to characterize its sorry. Okay, so this will be P out. Okay, and this will be V in, of course, in this case. Now, one way to do this, if you, in a very practical sense, if you want to make your simulation easier and much faster, you can actually, instead of giving a modulated signal, can you actually give a DC input? What happens if I actually make this VDC and vary this VDC input at the baseband? Instead of giving it a time varying sinusoid, if I just give it a DC, what happens? The output, first of all, if I just give a single DC, what will the output be? It will be a single tone. It will be a single tone at the LO frequency. I will not get a modulated tone, I will get a single tone. Okay, I can choose to do this many ways. I can choose to give a real modulated signal. I can give a sinusoid, maybe of varying frequencies. I can give a DC also. But even if I given a DC input, because I have this up converter in there, which is mixing it with the LO, I will actually get a single tone signal. And if I vary this VDC, what will happen to the output power? The output power will also vary, because this VDC I am giving in here, it's a differential VDC or IDC. This is an estimate of how much differential signal is actually going into the up converter. Okay, and so that will actually vary the output power. So this is an easy way to characterize the AM/AM or AM/PM characteristic of the transmitter, overall transmitter. Very quick way of doing it. Now there is one thing you have to take care of. When you do this, you have to be a little bit careful about the output power levels versus the input DC quantity. Because if you take, let us say, a DC signal and apply it to this, you will get a certain output power. What am I, at the end of the day, I am interested in transmitting a certain amount of output power. Maybe, I don't know, 10 dBm, 20 dBm, 30 dBm. At the end of the day, I want to characterize the transmitter at the maximum output power. what I need to do is correlate the DC I have to apply at the input to get the same amount of maximum power for the single tone as I would have got if I had applied a modulated signal. How do I do that? What decides that value? Correct. So what you really need to do, the output power is really a function of the RMS value of the signal going in to the baseband. RMS value of the modulated signal going into the baseband. Okay. Now the peak power at the PA output will be related to the peak, right? The average power is related to the average value going in. So you will find many people talking about what is called a PAPR or PAR and so on. Okay. This refers to the peak to average power ratio. Okay. Now different signals, depending on the modulation scheme you use, different signals can have different peak to average ratios. In some sense, if you want to get a certain output power, the RMS signal going into the baseband is only a certain value. However, if your system is not linear enough, when the input signal transitions to its peak value, your transmitter might clip it. Okay, and it will look very non-linear. So your transmitter is built for a certain average power, but it should also be able to handle the peak power. So when you say the average power at the output of the PA is, or the RMS power is 20 dBm, the peak power may be higher. Understood? And that is what you mean when you say it's a linear amplifier. The clipping, the amount of clipping you see on the peak signal is, you might get some clipping, but that amount of clipping is acceptable because it might degrade the error vector magnitude, EVM, of the signal, of the transmitted signal, only by a very small amount. Now the more you clip it, the worse it gets. As simple as that. Okay? So now you need to worry about this peak to average power ratio. And what is the peak to average power for a DC signal? It's 1. Okay? So PAPR DC is 1 or 0 dB. If I have a sinusoidal signal, what is the peak to average power? The amplitude is 1 over root 2 times the peak. If I take a modulated signal, it can be much higher. Okay, so let us say we take an LTE signal. The peak to average power ratio could be maybe 10 to 12 dB. Okay, and you have to be careful about some of these terms, because many people prefer, for a modulated signal, they prefer to refer it not to the DC signal but to a sinusoidal signal. So even though the peak to average ratio is 12 dB, somebody might tell you it's 9 dB because they might have referenced it to a sinusoid or a continuous wave signal. Okay. If this is the case, you have to apply an appropriate DC which will give you the same amount of output power. You understand? You will have to apply a much smaller DC to get the same amount of output power. Now you can actually vary this DC to get your AM, PM characteristics of the amplifier. Understood? So if it is for a, if you are doing this, you could do this if you are talking about a transmitter with an up converter. Obviously, if you just take a power amplifier and do it, this won't work. Okay, you try to put in DC, you will only get nothing at the output. Okay. No. So when you actually get this characteristic, okay. So you take this guy. Your average power may be here, but you have to characterize it till it clips. Okay, so see, first of all, the characteristic of a transmitter is the output power. As soon as you have normalized the V in DC to whatever output power you need, you really need to make sure that you get a certain, so maybe this is, let me call this the peak, maybe this is the average. Maybe you get some amount of clipping. You have to, no, well, it depends on what you are characterizing. If you are drawing the AM PM curve, you are going to be sweeping the input DC. It's not held at a particular quantity. You are sweeping it and you have to sweep it at least till the peak value, if not more. Okay? You have to sweep it at least till there to get an understanding of how the system behaves. Is that clear? Okay. So we will quickly start off with the RX architecture. As many of you know, this is also called by many other terms, homodyne or zero IF and so on. Okay. So you have your antenna, and of course you might have a duplexer and so on, but primarily the receiver will consist of some filtering, LNA, and maybe this band pass filter is provided by the duplexer itself. Right? The duplexer has a certain frequency characteristic, so that may actually be your duplexer as well as a band pass filter by itself. So then you take your LNA output signal, you need to send it through a mixer. What kind of mixer would you send it through? You need to send it through a single sideband mixer to regenerate both the I and Q components of the receiver. So I'm going to multiply it with cos omega LOT and sin omega LOT. I take the two outputs, maybe I have some gain, maybe I have some low pass filtering. Okay, and really these two will give me the I and Q outputs of the receiver. Okay, so I am going to look at the signals at A, B, C, D. I can very easily do that. I'll assume that the input has a certain characteristic, maybe cos omega RFT. Omega RF will be the same as omega LO, and then I can find out what happens. So let us say your received signal was, I'll write it in the polar form. You can write it as anything, A of t cos omega LOT plus phi of t. You can write it as the in phase and quarter share components also, doesn't matter. This is the received signal at this point. At A, okay, the signal will be x of t times cos omega LOT plus theta. Correct? I have just mixed it with cos omega LOT plus theta, and I can split it as the two components, half A of t into the low pass component. Omega LO is the same as omega RF. I'll get cos phi of t plus theta plus 2 omega LO t plus phi of t plus theta. Okay. I'll get the omega 1 plus omega 2 and omega 1 minus omega 2 terms. Then I'm going to maybe amplify it, low pass filter it, and so on. We'll also make the assumption that theta is 0. We'll see what this theta is. So what does theta represent? Phase difference between what? So yeah, so you don't know the phase of the incoming RF. The phase of your LO generated is going to be tied to some phase reference, maybe a crystal reference, right? Which will obviously be completely different from what you are receiving. So in a general sense, the phase of the received signal is going to be at an arbitrary phase compared with the LO signal. So that is why we have this theta here. So first what we'll do is we'll assume that theta is 0. Okay, we'll assume theta is 0, see what happens. Actually, so far in all our calculations, in the mixer and so on, we've been assuming theta is 0. Right? So let us first assume theta is 0, do what we did, then we'll see what happens otherwise. So if you look at after low pass filtering, you get half A of t cos phi of t. Similarly at D, you get minus half A of t sin phi of t. Okay, so you have managed to get the in-phase and quadrature components in some form or the other. Now you want to demodulate this. You want to get the signal. How would you demodulate this? You have I and Q. How would you demodulate the signal? Correct. So square root of I square plus Q squared will give you the amplitude and tan inverse will give you the phase. So that is one easy way to extract the amplitude and the phase. Here we are assuming that we want to extract the amplitude and the phase. So your demodulation algorithm could be, so let us say C squared plus D squared so half A of t, this will be your AM component. Then remember, this tan inverse now needs to be a 4th quadrant tan inverse. That is extremely important. So you have to be careful about the phase, otherwise you will get a 180-degree phase shift. No. This is extraction in the digital domain, but I am just showing you an example of how you would extract it. You would probably have an ADC, digitize it, and then you can do exactly this in the digital domain. So at the end of the day, whether it's digital or analog, we want to extract the amplitude and the phase. We would never or almost never extract the any information in the analog domain. Okay, especially because the modulation is in a digital form. There is no use demodulating the analog component. Okay. Okay. So now it's very easy to see how you would demodulate it. Okay. Now, there are two cases to consider. So, first of all, do you really need both I and Q components? So, let us say I have only one component. Can I actually get both the amplitude and the phase? If theta is 0, let us consider that case first. The second case is when theta is not 0. Let us say theta was 0 and I had only one channel. Can I actually extract both the amplitude and the phase? Exactly. So primarily, if you just choose one of them, you won't get a 4th quadrant tan inverse. Okay? Because this cosine phi of t is not unique. If it's positive, it can be positive in 2 quadrants. So that is one problem. Because if you have a true xi and xq, it can have independent amplitude and phase. Second thing is, your xi and xq can have, here we have taken a case where the modulation was purposely split into amplitude and phase. I could as well have written it as xi of t and xq of t. Xi and xq may be independently modulated. If that is the case, you definitely need both channels.